Hello, this is Mahanda Didia. This submodule is incorporated in book on liquid formulation. The discipline involved in integrated approach of development is critical, and it's the main focus of this book. This submodule will focus on classification and type of emulsions. Orientation of emulsifier at the interface is extremely important. It defines the type of emulsion. The properties of emulsifier, its hydrophilic, lyophilic property, and volume fraction of the oil phase and the aqueous phase will define what type of emulsion will produce. In a simple oil to water emulsion, an emulsifier lyophilic part is inward at the interface. In water to oil emulsion, the continuous phase is oil, and lyophilic part is outward at the interface. So these two emulsions, from physicochemical perspective, appear different. Oil and water will appear like a golf ball. Water in oil will have a spiked surface. The type of emulsions will depend on water and oil content, or aqueous and oil phase, and emulsifiers. In this case, globules are of aqueous or water phase. Oil in water, the globules are made out of oil. And then there are double emulsions, or emulsion within emulsions. These are characterized by coexistence of an emulsion globule within an emulsion. In double emulsion, it's an emulsion acts as a globule. And this first phase, therefore, can be oil and water or water and oil emulsion. The continuous phase could be water. In that case, it'd be water, oil, water emulsion. Continuous phase can be oil. In that case, it would be oil, water, oil emulsion. Continuous phase can be silicone or silicone related compounds, which are very common in cosmetic industry. These would be oil, water, and silicone. So first layer of water is a core layer. Oil layer is a shell layer, and the final water layer in a continuous phase. Look at details of how the orientation of emulsifier takes place in these double emulsions. And we will take water, oil, water as an example. This is applicable to all other types of double emulsions. The composition at the interface has three components: core or inner water phase, W1, oil phase as depicted by yellow, and outer water phase, that is a vehicle phase or external phase. At the interface between core, i.e. inner water phase, and oil, these are lyophilic uh, emulsifier towards oil. The tail will orient towards oil. On the shell, which is oil phase, and the water phase, which is external phase or vehicle phase, emulsifiers are hydrophilic emulsifier. And hydrophilic emulsifier head will orient towards the water, and a smaller tail entering into oil. This is idealized interface. actual interface, emulsifiers will distribute between phases. In addition to that, there's a capillary force between external vehicle water phase and internal core water phase. We need to put osmotic substances to balance the pressure. Let's look at the formation of multi. Please notice that within very short duration, within the bubble here, within the main emulsion, each of these are slightly separate emulsions, you will see formation of globules. And now you start seeing the formation of globules. Each of them are showing different types of globule formation. That's by design, slightly different emulsion properties. And I'll stop the video here for a second. See the globule formation. Emulsion formed within an emulsion. This is a double emulsion. Emulsion can be classified by droplet size. And it's very important to understand that because stability of emulsion not only depends on oil, water, and emulsifier, but its droplet size. Macro emulsion, classical emulsions, the creams and lotions, their droplet size exceed micrometer mm, and they are produced by mechanical agitation. They range from 1 to 100 micron and can go even as large as 500 micron. Nano emulsions are extremely popular. They are commonly used in pharmaceutical and cosmetic industry. Droplet size ranges from 20 to 500 nanometer, and it generally requires additional mechanical energy to make it, or there are other ways to do it. The most interesting are microemulsions. They are not single phase. There are three different components in there. They're biphasic, two phases, but they behave like a single phase because of surfactants used. Microemulsions are not necessarily spherical, and they're typically very small, 10 to 15 nanometers. And microemulsions are thermodynamically stable. That's the main advantage of microemulsions. We look at it in this pictorial. Macroemulsions, or what we call conventional emulsions, they have large particles, small particles, and their polydispersity is greater than 40%. They are typically not thermodynamically stable. That means eventually they will separate into oil and water. They are kinetically weakly stable. That means over time they will separate, but that time frame is adjustable. Nanoemulsions, they are very popular in cosmetic and pharmaceuticals. They are spherical. They are thermodynamically unstable. That means they will eventually separate. However, their shelf life is much longer than macro or traditional emulsions. And their polydispersity, i.e., the globule size, is fairly uniform compared to macroemulsions. Microemulsions, these are 10 to 100 nanometer. They can be spherical or lamellar. They are thermodynamically stable because they are very small. They behave like pseudo monophasic system, and their dispersity is even much lower than nanoemulsion. The phase diagram above, we can see water and oil, microemulsion. This is a very narrow range within the phase diagram, surfactant, water, and oil. And oil in water microemulsions are formed again in a very narrow range of it. There are micellar solutions and there are reverse micellar solutions. So microemulsion domains are very small. To look at it physically in this slide, we can see macro or emulsion, a classical emulsion, nano emulsion, and microemulsion, which behaves as a pseudo single phase. So if they behave like pseudo single phase solution, then they would have a higher clarity. As it can be seen through these green lines here, microemulsion has a very good clarity compared to nano, which has a reasonably good clarity, and emulsion, which is traditionally classical emulsion, lines will not appear. So these are critical properties of emulsion. Nanoemulsions are emulsion, microemulsions are emulsions. That means oil, water, and surfactant, and oil for oil and water will be a globule. There are other physical properties of emulsions that are covered in pre-formulation section. Zeta potential, uh, that allows us to measure kinetic stability of emulsions when ionic surfactants are used. Optical microscopy, you saw some of that formation of double emulsion. Physical stability of emulsion droplets, we will again go more detail in pre-formulation. And rheological aspects of emulsion and viscosity, extremely critical for cosmetic formulation and pharmaceutical formulations. We'll go more detail in pre-formulation submodule of emulsion. Separation of emulsion, i.e. breaking of emulsion into oil and water. Gibbs thermodynamic theory will tell emulsions are not thermodynamically stable. The phases will eventually separate. The kinetic stability of emulsion is governed by many rules, and Stokes' law for suspension can be applied to emulsions. In that case, size, density, and viscosity will play important part in stable emulsion formation. In addition to that, zeta potential, uh, efficiency and quantity of emulsifier, how efficiently emulsifiers cover the interface, is very critical for the stability of emulsion. In addition to that, temperature, agitation, vibration, pressures, dilution, evaporation, all those will impact emulsion stability, and we will cover that in pre-formulation submodule. Emulsion cannot be separated by gravitational force alone. So in next chapter, we'll look at pre-formulation in far more detail.